In this video, we're going to be talking about a very important property of graph neural networks called equivariance. And if you looked at model architectures for modeling atoms, you probably have heard this term a lot. So what do we mean by equivariance? Well, equivariance means that if we take the inputs, say the atoms, and we rotate them, is that the output of the network and the internal representation of the network will be transformed accordingly. So let's start off by talking about a couple simple examples, and then we're going to dive into what spherical harmonics has to do with all this, and finally we'll wrap up with a discussion about model architectures. Let's just look at a specific example, like translation equivariance. So let's say we have, a nice cute dog like this one, we have a picture of it, and we have a function f which can segment out that dog. Now if we take that image and we translate it, and we apply the same function to segment out that dog, and then we translate it back, if we get the same answer, then we say that that function f is equivariant with respect to translation. So why is equivariance important for object detection? Well, it is, a mathematical property. We know it's something that should be true, but the real reason is actually a more subtle one, which is the following. If we have a bounding box, let's say in the image here, we don't have to learn a new set of weights to detect a dog in this bounding box versus this bounding box, or this bounding box, or this bounding box. We just want to learn a single object detector that works across the entire image and can work regardless of whether the image is translated left, right, up or down, etc. So the way that we do this is we use a convolutional neural network, or a CNN, where we break the image up into a grid, we compute a function then at every single grid cell, and then we get an output map. And this output map is essentially, translation equivariant because it's going to shift as the image shifts. And this is a really nice property for CNNs to have. It's a lot more efficient for them to learn, and this is why CNNs work so well and why they're so popular in the computer vision community. So how does this translate to atoms? Well, the first thing is we don't really care about translation equivariance for atoms. What we do care about is rotation equivariance. So imagine we have a set of atoms like you see here. We have a function f which computes the forces on these atoms. Now if we take those atoms and we rotate them, and then use the same function f to compute the forces, and then rotate the forces back, we should get the same answer. So this isn't a property that we would expect a neural network just to have naturally. Because a neural network, all it does is it takes these atomic numbers and 3D atom positions as inputs, and then just computes some arbitrary output. It doesn't know that the 3D atom positions are anything special. They're just a set of numbers that it's looking at. So as we rotate the atoms around, from the neural network's perspective, those atom positions are just kind of changing kind of randomly, until it learns anything better. So what was nice about the CNN is we didn't have to learn a new set of weights to detect a dog in different positions of the image. Similarly here, what we want to do is have an equivariant GNN that doesn't have to learn how to estimate the energy of forces on a set of atoms for every possible rotation of those atoms. So how do we do that? So what is the best representation? Well, let's go back and look at our image example. Here, an image is represented by a series of planar channels, and this makes a lot of sense because we care about information in different parts of the image. But what representation should we use for atoms? Well, for atoms, what we care about is the information around the local neighborhood of the atoms. So instead of planar channels, what makes more sense is to use spherical channels, where each point on the sphere basically indicates the information at different orientations from the atom. So let's look at how both of these representations handle equivariance. So in the image case, our embedding is a planar channel, and when we translate the image, the embedding corresponding to that planar channel is going to translate as well. Now in the atom case, we have a spherical channel, and here we don't care about translation equivariance. What we care about is rotational equivariance. So if we rotate the set of atoms, then what we want is the spherical channel to rotate similarly. So just to give you a sense for what these spherical channels should hypothetically look like if we have a system and it's all rotating, and what you can see here is that as we rotate the entire system, that the spherical channels rotate accordingly. How do we represent our spherical functions or our spherical channels? Well, if you have a computer vision background like myself, the first thing you might think of is to discretize the sphere. So basically you have different points for different longitudinal or latitudinal points on the sphere. So if we need to rotate the system, that means that we have to resample the sphere. And whenever we resample, that basically introduces errors and blurring. So this isn't ideal. Instead, what we do is we represent the function on the sphere using a set of basis functions and coefficients, where here x are the coefficients and y are the set of basis functions. So what do we use as our basis functions? Well, we use the spherical harmonics, where every basis function has a degree L and order m. And as we increase the degree L, the resolution of the basis functions increases. So you can look at this as representing higher and higher frequencies of the underlying function that we might want to represent. Now, you might look at the spherical harmonics and think, well, it looks like a bunch of sine or cosine functions on a sphere. And if you see that, your intuition is correct. If we actually look at the functions themselves, the L equals 0 coefficients are just a constant. If we look at degrees L equals 1 and L equals 2, we'll see that these are basically functions that are sine and cosine of different angles on the sphere, theta and phi. There is one really interesting property of spherical harmonics, which is why we use them for this application. As we already discussed, you can use spherical harmonics to represent any function on the sphere using a set of basis coefficients. Now, what is amazing is what happens if you want to rotate that function. To do this, you can simply multiply the coefficients by an appropriate matrix, referred to as a Wigner-D matrix. For any rotation you want to perform, there exists a unique Wigner-D matrix which will transform the coefficients to represent your desired rotated function. This is really cool, since it means you can rotate the function perfectly using just a simple matrix multiplication. This might seem a bit magical, so let's dive into the mathematics behind this just a little bit more. And to do this, let's look at a simple problem to gain some intuition. Let's say we have a 1D function here f, and we want to translate it to the right. How do we do this? Well, first off, let's represent this function in the same way we represented the spherical channels, using a set of basis functions. We can do this by splitting our function f into a series of sinusoidal functions using the Fourier transform. If you're not familiar with the Fourier transform, I'll put a link in the video description below so that way you can learn more. So doing a Fourier transform, we find that we can decompose our function into a series of sinusoidal functions of the following form, where it's basically a magnitude times, let's say, a cosine, and each cosine is of a different frequency and has a certain phase offset. And you think of the phase as just kind of shifting the sine or cosine function, left and right. Now, when we want a set of basis functions, we want it to take the following form, where we just have a single scalar, x, multiplied by the basis function. Unfortunately, the functions I just showed here are not of that form. We still have that x, which is our scalar, but we also have the phi, which is our phase offset. And we don't want phi, so we need to figure out another way of formulating these functions to make them into a true set of basis functions. So in order to understand how to do this, let's look at a special property of sine and cosine functions. So if you take a sine function and you take a cosine function and you add them together, what do you get? Well, you get another sinusoidal function. And this is true for whatever sine or cosine function you use. As long as they are the same frequency, they can be at different magnitudes, they can be different phase offsets, etc. If you add together multiple sinusoidal functions which have the same frequency, you're going to get another sinusoidal function out. And this is really surprising. This is something else that I don't think it's that intuitive, but the mathematics work out. So specifically, what's interesting here is the following equation, which is the cosine of theta plus phi is equal to a linear combination of sine of theta plus cosine of theta, where A is equal to sine of phi and B is equal to cosine of phi. Now let's see this in action. So what we see here is something pretty cool. You can take a linear combination of a sine and cosine function, add the two together, and you get a shifting cosine function. All right, so now let's go back to our original equation f, and we broke it before into 4 different cosine functions. But what we want it in is a different form, where it's a set of basis functions that don't have that dependence upon phi. Well, using that trick we just showed, we can basically break apart each of those cosine functions into separate sine and cosine functions. So now instead of having 4 functions representing f, we're now going to have 8 functions representing f. And this forms a good set of basis functions, where we have 8 different basis functions equaling sine and cosine at different frequencies, and then we have the different coefficients that we multiply by these basis functions to then produce our function f. All right, so now we have all our basis functions. We have a way of representing f. So how do we actually get it to translate by, let's say, a certain amount alpha? So in order to understand how to translate this function, let's just look at two of the basis functions. And if we just wanted to translate it to the right by alpha, what we would do is subtract off alpha from theta from each of those equations. Pretty easy, right? But again, we don't have it in a nice form of basis functions. But we can apply the exact same trick that we just did, where we just have cosine of theta minus alpha is going to be equal to sine of negative alpha times sine of theta plus cosine of negative alpha times cosine of theta. We can do the same thing for all the other basis functions, and if we put this into a matrix form, we can get an 8 by 8 matrix, which is block diagonal with 2 by 2 blocks. And we can multiply that matrix times the coefficients, and then use that to scale the basis functions and sum that all together to then create a shifted version of our function f. So hopefully this formulation looks pretty familiar, where we have a matrix, we multiply it by our coefficients, which then get multiplied by our basis functions, we sum it all together, and this results in a shifting equation. This is exactly what we saw before with the spherical harmonics, where we had the Wigner-D matrix, which we multiply by the coefficients times our basis functions to get our rotating function on the sphere. The same underlying principle that we just used for the 1D function, but applied to a sphere. It's a little bit more complicated because we are representing a function on a sphere, and that's why the block diagonal matrix has varying sizes for a different L, but the underlying principle is exactly the same. So while we're talking about mathematics, let's make the concept of equivariance and invariance very concrete. So what we have is we have a function f, which we use to compute our embeddings x. And f is a function of both the z, which is our atomic numbers, and v, which are the positions of the atoms. Now, if we have an invariant representation, f is going to have the following property. If we rotate the position of the atoms by some rotation matrix R, this will be equal to f if we just pass in the atomic numbers and the original positions v. Because we know if you have an invariant representation, if you rotate the different atom positions, this isn't going to impact the representation x. Now for equivariant representations, if we rotate the position of the atoms v by some rotation matrix R, this is not going to result in exactly the same representation x. So for equivariant representations, if we rotate the atom positions by some rotation matrix R, this is going to result in the representation being rotated as well. And here the rotation is going to happen using the Wigner-D matrix that we mentioned before. Okay, now let's take a step back and look at how we actually perform message passing in an equivariant neural network. So when we do message passing, we have two atoms, one which is a target atom, which will be the red atom here, and we have a source atom, which let's say is a gray atom. Now, if we look at this, there's actually 6 degrees of freedom in this system, where we have 3 degrees of freedom from translation and 3 degrees of freedom from rotation. But we can remove a lot of these degrees of freedom if we create a local reference frame. For instance, we could take the target atom, which is the red atom, and position it at the origin of our local reference frame. And this basically removes 3 degrees of freedom, and this leaves us 3 final remaining degrees of freedom due to the rotation. But we can get rid of some of these by aligning the y-axis with the gray atom. And this leaves us with just 1 remaining degree of freedom, and that's the rotation about the y-axis. So if we want to have a neural network which is equivariant, we need to make sure that we are equivariant with respect to that final remaining degree of rotation. And the way we do that is by performing a convolution about that final degree of rotation. So how do we do that convolution? Well, let's look at how we do convolutions for images. So if we do a 2D convolution with a CNN, as we mentioned before, we basically compute the same function in every position at the image, and this gives us a response. And we can look at this as basically having our image G. We can then convolve it by some filter H, and in this case, we have a blurry dog. We could do something similar with our atoms if we wanted to. So basically, we just need to perform a convolution around that remaining degree of freedom. We could just compute a function at every single orientation and then sum them together and do the convolution that way. But as you might expect, it's kind of expensive to do it this way. So going back to our 2D example with images, there's an alternative approach which uses the convolution theorem. And what this states is that you can take the image and perform a fast Fourier transform to transform that image into Fourier space. You can then just do a pointwise product with a filter, which is also in the Fourier space. then perform an inverse Fourier transform to transform that image back into the spatial domain. And that is your convolved image. The same thing we saw before, but done very differently. And the convolutional theorem basically states that a convolution in the spatial domain is equal to a pointwise product in the Fourier domain. So in many cases, it's much more efficient to do a convolution in the Fourier domain than it is in the spatial domain. So let's go back to atoms. How do we use this observation for our problem? We have two atoms that we'd like to pass a message between. We can rotate these atoms so that way they align with the y-axis using the Wigner-D matrix. Then, we just need to perform a convolution along our remaining degree of freedom, which is a rotation about the y-axis. So let's look at our actual spherical harmonics, the basis functions that make up the spherical channels. If we look at these and we examine how do they change as we rotate about the y-axis, we notice something really interesting. For the m equals 0, the spherical harmonic coefficients with order 0, what we notice is that their values don't change as we rotate about the y-axis. They're actually constant. If we look at the m equals 1 and -1 coefficients, what we find is that their values change based upon sine of phi or cosine of phi. We go the next order out, we find that they vary based upon sine of 2 phi or cosine of 2 phi, etc. We can see this as well if we look at the equations. And if we say that we're only going to rotate about phi and we're not going to worry about theta, we can rewrite our function as a 1D function in the Fourier domain, just a linear combination of sine and cosine functions like we were talking about before. And since our function is already in the Fourier domain, we can do a convolution really easily by just doing a pointwise product of the various coefficients. And the coefficients here are the a's and the b's. So just a couple words on how we do a pointwise product. So we have an embedding x, which is indexed by the degree L, the order m, and the channel C. And then we have a filter, which is indexed by L, M, and C, as well as L prime and C prime. So if we want to do a pointwise product for the m equals 0 coefficients, we can just use the following equation where we're summing over all L prime and C prime, and it's fairly simple and straightforward. However, it gets a little bit more complicated for the coefficients which have orders greater than 0 or less than 0. If we just do the naive thing, that's going to be incorrect. Because the way you should actually think about it is that the coefficients are actually complex numbers, where the real and imaginary parts are the negative and positive orders. So when you do a pointwise product of complex numbers, it's a little bit more complex, and you just follow the equation that you see here. If you're curious to understand this more, you can go check out the code, and you can see how this is done. One other thing to mention is that in a lot of equivariant papers, they use something called a tensor product. And I'm not going to go into all the details behind the tensor product. It can be a little bit complex to understand, but it has the same underlying inputs as what we've already discussed, where you have the embeddings x, you have the filter here, which is shown as h, you have the basis functions y, etc. But what's interesting is actually that the tensor product does the exact same thing that we just described. The thing you should know about a tensor product is that in its general form, it is order L to the 6th power to compute, which is computationally quite expensive, and is the reason why most equivariant neural networks that were out there before generally only had degrees up to L equals 2. But the trick I just described of rotating the spherical harmonics to the y-axis and then converting the convolution problem to basically a bunch of 1D convolutions is exactly the same as doing a tensor product, but instead of being order L to the 6th, it's order L cubed. So this is much faster. And you can see here, just illustrated, that performing a tensor product using this other method is much more computationally efficient and allows us to use much larger L, higher resolution, which results in general and better accuracies. All right, so just following up on a few loose ends. I haven't talked about how we perform a nonlinear activation using equivariant neural networks. One way to do this that we use is, let's say we have a spherical channel, is we project that onto a grid, and we basically perform a 1-by-1 convolution on this 2D grid using some nonlinearity, and then we project that back to the spherical channels. Easy enough. It would be nice to have a slightly better way of doing this where you didn't have to project it to a 2D grid, but for now, this seems like the best method that works. All right, now we have all the pieces. We can finally describe the overall message block that we use. So here we have a message block where we have function f. It takes as input the distance between the atoms as well as their atomic numbers. First thing we do is multiply the two embeddings, xs, which is from the source atom, and xt, which is from the target atom, by the Wigner-D matrix to rotate them to the y-axis. We then compute an edge embedding from the distance between the atoms and their atomic numbers. We use this and feed it into two convolutions that we just described. We sum these two together and then perform our nonlinearity. We then rotate it back to the global coordinate frame, and we get our final output message. And that's it. That's our model. And if you want to learn more, this model, which we call the ESCN model, is described in the paper below. The mathematics drill in there is a little bit complex, but hopefully this video made it a lot easier to understand how this model actually works. Finally, one thing that's important to know when you're using equivariant neural networks is that you're placing pretty hard constraints on the types of nonlinearities and the types of functions that you can use. And this has the potential to hurt the overall expressivity of the neural network. In this video, I described one particular network, but there are a lot of other really interesting equivariant neural networks out there. If you really want to get a good overview of all the different possibilities, check out some of these other papers, and I'll put some links in the video description below as well. We've been talking a lot about models that are provably equivariant, but do they actually need to be strictly equivariant? If we go back to our image detection example, we were talking about translation equivariance, and that's a nice property to have. But in general, in computer vision networks, it's not scale equivariant or rotation equivariant, it's just translation equivariant. And the way that these models still work, even if, like, say, the dog in the image gets larger or smaller or rotates, is that there's enough training examples that it kind of learns automatically how to detect dogs in different scales or different rotations. And we could do the same thing here for atoms. We could just take our data, take our training data, and rotate it in arbitrary ways, and we can just hope the network learns a fairly invariant or equivariant representation. And this will get you pretty far, and there's a couple different papers out there that are taking this approach. And who knows, maybe this is the right way to do it, and not having it baked in, strictly mathematically into the neural network. So, are you curious how well these models actually work? Well then check out our next video, where we're going to be talking about evaluation metrics, data sets, and how well these models actually work in practice. And we'll close by discussing some of the remaining open problems. See you there.